So today this session we will be discussing about the manometers and the types of manometers. So what exactly these manometers are? So previously you might have heard about the barometers. You might have heard in your physics or temperature what exactly the barometers are. But today's topic is about the manometer. So these manometers are the very simple and easy in construction devices which are used to measure the pressure. At a point in a fluid. But here the condition is the fluid should be considered in an equilibrium. Then these manometers can be best utilized to determine the pressure available in that. Right. So now we're coming to these manometers. How do these manometers look like, and what are the types of manometers? So is there any types of manometers? As the heading says, it's a manometers, right? So these manometers are categorized basically two types. So one, it is a simple manometer, another one is a differential manometer. So what is a simple manometer? Consists of a glass tube having one end open to the atmosphere or open to the air, where the pressure is allowed to measure it, and other end it is completely closed, right? And whereas the differential manometers are concerned, they are used to measure the difference in the pressure at 2 points. So that means directly they are not measuring the pressure, but they are just evaluating the difference in the pressures in the differential manometer. So that is the reason they have named it as a differential manometer. And the simple manometers are used to directly measure the pressure, as the construction I have just explained about. Now coming to the pressure measurement by the manometers. So what is the relationship between the manometers and pressure measurement is? So here we will be gauging this liquid. Here we are using the liquid gauges, and using this liquid gauges we are measuring the pressure. So coming to the manometer types. So manometers can be single tube manometers or single column manometers, or it can be initially it will be called as a piezometers. Right. So piezometers, U-tube manometers, and single column manometers, and these U-tube manometers are also called as a multi-length manometers. Multi-tube manometers also it will be called as. Right. So piezometers, U-tube manometers, single column manometers, and multi-tube manometers are also available, right? Or also can be used to determine the pressure at a single time. If your interest is to measure at a 30 points, 10 points, 5 points, then we can arrange this U-tube manometers and we can get the at a single time we can get the readings of it at the 5-point location zero. So this is exactly defined based upon the column zero. So it is a single column manometer or it is a multi-column manometer. So let us go in detail about the piezometer. I think everyone would be comfortable or knowing it very easily. What exactly the piezometer? So as we can see in the construction, or as we can see in this image, the piezometer is actually the construction is being explained. So that one head of this particular one is open to the atmosphere, so that here we can see as the arrow mark indicating in this one. So here it is open to the atmosphere, and the other end it is completely closed. Inside this one. Right, this is the construction of a piezometer. Now my interest is to know the pressure at the point B. So here we have defined two heights. So what is the h1 from the point to the level of this circumferential of the circle. So that is the point A, and where the B is available, that height is represented as a h2. So we have represented, or we have noted that heights from the free surface level to the point A it is h1, and from the free surface to the point B it is represented as a h2. Right. So this is a simple construction of a piezometer. Right. So using the simple piezometer, how do we measure the pressure? The next question comes: how do we measure the pressure? And whatever the pressure we are measuring, the measured pressures using this equipment or using the manometers are called gauge pressures. They are the gauge pressures. They are not the absolute pressures, but they are the gauge pressures we are going to measure. Now, since we have noticed that there is a difference in the point A and point B, now my interest is to determine the pressure at the point B. Point B. Right. So pressure at point A. So let us write the equation according to the hydrostatic law. P is equal to rho GH. P is equal to, as the pressure varies only with respect to the height. as the pressure varies only with respect to the height. So we can say that the pressure at point A is equivalent to rho GH, where the rho remained constant, that is the rho represents the density, and G is the gravitational field, and H is the height involved in that. Right, so pressure at point A is equivalent to, so here you can see, so let me annotate it and show you again. So here you can see that the height involved in this one is up to the H1 height. So that is at the point A. So that is what we have represented. PA is equal to rho G H1. And similarly, for a point for the point B, the pressure available at the point B is directly, that is according to the hydrostatic law, we can simply write PB is equal to rho G into H2, rho G into the H2. So this method can only be used for the liquids, but we can't use it for the gases. Very important, and the point to be noticed here in this one is this method of measurement of the pressures can be used only for the liquids. When we are using the gases will escape out. So we can't measure the pressure when we are using the gases, right? And so here in this another criteria is this is piezometers where it is open to the atmosphere. Now my interest or my requirement is being satisfied. Pressure at a point A is rho into G into. If the H1 is known, then definitely I will be knowing the pressure at point A. So the density here, the density represents density of the fluid present inside. And the G is the gravitational constant, so which is acceleration due to the gravity, which is equivalent to 9.81. Similarly, at the point B also we can measure the pressure available. So that is at the point B is equal to rho G H2. Okay. So, but one condition it is given here, it is not useful for the gases. For the gases we can't measure by this method. Coming to the other type of manometer, so which is mostly used or most common applications in nowadays or today, the manometers are being replaced, but the basic principle remains same. That is a YouTube manometer. That's a YouTube, as the name itself says, YouTube manometer. So second category of the manometer we are discussing here. First was a piezometer, and second one is a YouTube manometer. So this YouTube manometer enables us to measure the pressure in between the 2 points, or the difference of 2 points can be measured by using the YouTube manometer. It's the same instrument, and we can understand better by seeing the construction of the YouTube manometer. See here. So here in the example, you can see there is a YouTube manometer. So let me annotate it and show you. So this is what exactly it looks like. So this is our YouTube manometer. This is a construction of a manometer that is a U-like shape in that one. So what is my interest in this one? What is my interest in this one is I'd like to know the pressure at point A. I'd like to know the pressure in between the point A, so that A is at the equilibrium point. So if you see, so A is exactly equivalent to this height H1. Okay, A is exactly equivalent to the height H1, and at the B point, if you see, there are two types of liquids available in this one. So that means by using the YouTube manometer, we can even measure the pressure by using the two liquids. So it is upon the user requirement whether we are going for the two liquids or one liquid. So when we are using this, as it is zones are shown within two shaded colors. One it is a gray and another one is a dark black. So here in this you can see. So this region is shaded. So this we will call it as a manometric. This will call it as a manometric fluid. This will call it as a manometric fluid. Okay. So the manometric fluid is actually, so as I mentioned earlier, so whenever the manometer is being considered, so we have to get into the equilibrium. So we have to, where should I apply the equilibrium? The next point comes, where should I apply the equilibrium? So as this manometer and the fluid interface is available at the point B, as the manometer and the fluid interface is available at the point B, I'm taking at this equilibrium condition. I'm taking this as my equilibrium condition, and from there I have measured my height, and this height is being measured as H1 to the point A. To the point A it has been measured as H1, and to the point D it has measured as H2. To the point it has been measured as H1, and to the point D it has been measured as a H2 from the reference level or from the equilibrium level at the BC. So according to the Pascal's law, when the fluid container is completely closed, the forces acting upon that one will be under equilibrium. So that condition we are going to utilize here. So this states that at the point BC, at the point level of BC, the fluid will be under the equilibrium. So let us compare that one. So pressure is in a continuous static and in a horizontal level. So pressure at B is equal to the pressure at C. But pressure at B, see the bottom of it is remained same. The bottom of the fluid may be having the same pressure on this one, but here we have again height variation is present. So whenever the height is varied as per the hydrostatic law, so the pressure also should vary accordingly. So let us compare that one. So that we are going for the equilibrium of the pressure at B and C. So now we are going to apply the principle of equilibrium at the point BC. Right. So what is that is done in the pressure at the level or equilibrium level, pressure at B is equal to pressure at C. So that is PB is equal to PC. Okay. So by maintaining that equilibrium pressure on the left hand side, of the equilibrium, so the pressure available at the point A, it is the summation of the pressure available at point A plus the pressure available due to the height raised of H1, due to the pressure raised due to the height of H1. So there are one point A where it is actually having its own pressure, that is due to the Pascal's pressure, what we have discussed in the previous series or in the previous sessions. And now there is another pressure raised above this point, so that is PA plus, because of the height variation above this point B, so it has become totally PA plus, there is a pressure acting at a point A plus the pressure due to pressure above the reference level of B. So that is according to hydrostatic law, we can write PA plus rho G H1. PA plus rho G H1. Now on the other side, if you see the vertical column is open to the atmosphere. Here we can see that the vertical column is open to the atmosphere. So in this case, so when it is open to the atmosphere, that means atmospheric pressure will be acting on this particular fluid where it is open to the atmosphere, right? So but the actual pressure available at the point C, is equal to from the hydrostatic law, that is P2 is equal to, let us say it is a P2 at point C, or PC is equal to rho G, whether I have to write the same rho of the pressure available at the A liquid, or whether I have to change the liquid. We have to change the liquid, because at the point A, the liquid shaded and the arrows as shown in the representation, at A point and at the C point, the liquid is being varied, right? So here at the C, the liquid has been varied. So I have to write it as rho A, and here we are supposed to write it as rho C. So rho C, or the fluid which is available in this U-tube, right? So that let us write it as rho 2 G, that is a gravitational constant which is fixed, and H2, rho G H2. So from that one we'll get these terms as pressure available at B and pressure available at C. So pressure available at the B point is equivalent to PA plus rho G H1. So that means obtaining the equilibrium at this position. And on the right hand side, we have open to the atmosphere. So atmospheric pressure will be acting on that fluid. So that the atmospheric pressure will be acting over it, right? Since it is open to the atmosphere, plus the rho G H2, where the height involved due to the height raised by the H2. So that is on the left hand side and the right hand side. But actually, according to the equilibrium condition, we are supposed to equate these two in order to find out what is the pressure available inside. So let us equate this PB is equal to PC. Then we get PA is equal to rho G H2. So that means rho here it is being changed, and here the liquid which is available in the U-tube, we call it as a manometric liquid. So in the U-tube manometer, so whatever the shaded region, let us call it as a manometer. So that let us call this as a manometric liquid, and my intention is to find out the pressure in this fluid. So in that manometric fluid, so that I am representing with the density of the manometric liquid into the gravity into H2 minus rho G H1. So just I have equated these two equations here in this one. I just equated these two equations. Now your question, I guess, maybe, so where does when PP is equal to PC, so PA has come, rho G H2 minus H1 has come. But what about the P atmosphere? Why it is not available here in this one? Since, as I mentioned, we are measuring only the gauge pressure. Since, as I mentioned, that we are measuring only the gauge pressure. As we are measuring only the gauge pressure, that gauge pressure will not be addressing this particular term or the pressure here in this one. So that means here we have whatever the answer we have obtained. So that is the gauge pressure we have obtained. This we have obtained the gauge pressure. If you are interested to go for the absolute pressure. If we are interested in finding out the absolute pressure, just to sum up with an atmospheric pressure to this equation. So that is rho manometric GH2 minus rho GH1 plus the P of atmospheric. Then it will become your absolute pressure at point A, and that will become absolute pressure at point A. Now here we can reason out in the other way, like whereas the PA is not influenced by that particular force of the atmosphere. So that is also we can neglect this PA atmospheric. So that atmospheric pressure is only available where it is open, right? So but some will be arguing that if the atmospheric pressure is high, then the influence of the fluid pressure may be varying inside of it. Yes, so that is also true, right? Because as per the Pascal's law, the pressure force will be equally distributed in all the directions, So from that also we can say that this is only the gauge pressure which we are measuring it here in this one. So we got the pressure at the unknown point, that is P. This is how we approach in the manometers. So by first point is that identify the liquids available. Identify the liquids available in the manometer, whether it is only one type of liquid or two types of liquid or three types of the liquids. So first point, identify the liquids. And second point, you have to identify where the equilibrium position need to be. So we have to identify where the manometric fluid is imbalanced. We have to identify the point where the manometric fluid is imbalanced with the fluid there. So that's the second point. And third point, obtain these pressures into the equilibrium. Then finally you will get your resultant variation of the pressure, or the unknown pressures can be formed. Right. So if the fluid is measured in the case of a gas, for example, assume that it is measuring inside, it is measuring on the one side, it is gas, right? So then the density would be probably very low, and the density of the manometric fluid would be very high than the density of that one. So then we can neglect one term in this one, so that is rho g H1, because on the H1 side, if it is filled with a gas, so that we can completely neglect it, and finally our resultant equation we may end up with, PA is equal to rho manometer into GH2. But this condition is that on the H1 side or on the one side we have that it is a gas, and where the gas density is very less compared to the manometric fluid. In that case only the pressure is directly measured as PA is equal to density of the manometric fluid into G into the height. So that is H2. Okay, that is H2. So that is what about the manometer, YouTube manometer. How do we analyze, or how do we find out the pressure using the YouTube? So now next topic we are going to discuss about the single column manometer. So the single collimeter is nothing but a modified version of the YouTube manometer. So now why we are calling this as a modified version of the YouTube manometer? Let me show you in the picture in this one. So let us see the construction and then we can understand better. So as you can see in this image, so this one here, so the image, in the image you can see the YouTube, its constructions look like similar to the YouTube manometer, but we have on the right hand side one limb which is extended like a YouTube, and left hand side it is similar to the previous example, but we have one reservoir placed in between, and this reservoir area is 100 times greater than the right limb area, and the reservoir area is 100 times greater than the right limb area. So that is the difference between a single column manometer with the reservoir. Here this is also an example for the single column manometer, but it's a modified version of a YouTube manometer. Now the question comes, why we have went with this type of design? What is the need to go with this type of design where it has a modified version, or why do the reservoir is being added in this one? So when by using the manometers, we want to desiring the accuracy is very high, desired accuracy level is very high. In that case, people can go even with or we can go with a new design named as a single column manometer, where the reservoir is placed, which is area is greater, or the area is 100 times greater than the right column tube area, right? So as it is said in this one, so the cross sectional area is 100 times as that of the tube area, right? So where the change in the liquid, so when if you see in this case of single column manometer with reservoir, so the fluid level, whatever the pressure level, whatever the pressure it is being influenced on this fluid level, the area variation or the height variation would be very minute variation can be noticed here in this. So that is very minute variation, the height is can be varied. So that is being given by this delta H. That is given by this delta H. So where delta H accounts the small variation in the height due to the pressure variation, due to the variation in the, from the right limb to the left limb to the point. So when that reservoir will be utilized, where the delta H difference, the minute H difference or the height differences need to be noticed. So that we need to account it, or that in that cases we have to depend on the single column manometers. Now, so as far as the previous statement, so we need to approach for the fluid. I told 3 steps we need to analyze. We have to follow for all the manometers. First thing, identify the number of fluids available in the manometer. So here from the images we can see that one, it is a shaded color. So that let us say there's a water, and the black shaded one, let us take it as a manometric fluid. So there are 2 fluids in this one. So the black one, let us call it as a manometric fluid, and which is shaded, so that is dashed line. So let us call that it as a water. And the water level from the equilibrium. So here our equilibrium level is XX and the YY. So from the XX and the YY position, if you are taking the equilibrium level, so let us take the XX level is our equilibrium, where the manometric fluid is in balance with the fluid. So this is we have to notice it. So here one level we are balancing it. So this is very important. The second point would be satisfied from this one. So we are balancing at this point. We are balancing at this level, right? So at this level, when we are balancing the fluid, at this level when we are balancing the fluid, okay, so what is the equilibrium, conditions to be applied on the right hand side to the left hand side? So that is the pressure already available at point A. The pressure is already available at the point A. So that is PA. So this is the pressure available, and that is given by PA. That is given here, the pressure available in that one is PA. And if you see on the left hand side, PA, so then it is rho G, that is the density of the fluid on the left hand side, that is rho 1. Let us represent it as rho 1, density of the fluid. And generally from the hydrostatic law, we have to write it as rho GH. So writing in a similar format, it will become rho GH1 plus there is another variation, that is a small variation of the delta H. So plus it is rho G, that is rho 1G delta H, rho 1G delta H. So on taking these two common on the left hand side, our equation will become PA plus rho 1G delta H plus H1. Similarly on the right hand side when we move on, so it is rho 2 G H2 plus rho 2 G, what is that? That is a delta H. That is a delta H, because in between the variation of the X and Y, that is XX and the YY. So that small minute variation. So taking it out the common out, and then we are finding out the difference in between that. So that is the reservoirs are being utilized whenever there is a variation in this pressure level, and when we are constructing the reservoir, that is used to measure the minute differences in the pressure level. Right. So on obtaining the equation, so now my interest is to obtain the pressure at the point A. My interest is to obtain the pressure at point. So here we are interested to find out the pressure acting at a point A, but in this case the reservoir is being constructed. So in the case of the reservoir, what is the need of the reservoir? Why can't we go to the general constructions as like in the previous one? Means here we are in our interest is to know even that the finite variations of the pressure. That's a minute variations of the pressure. In order to improve the accuracy level in that one, the reservoirs can be adapted. But the construction of the reservoir area should be 100 times the actual tube area. That is the right limb area. Okay. Then obtaining the equilibrium, we have obtained the PA. So then if you see on the PA, that is the pressure available at the point A. Pressure available at the point A. If we expand this equation, and see, so that is simply delta H into rho 2 G minus rho 1 G plus H2 into rho 2 G minus rho 1 G1. As the volume of the reservoir remains same, the rise in the volume of the liquid is equal to the rise of the liquid in the volume, rise of the liquid volume in the limb, Okay, so this is what actually it is saying. But if in case now the question comes, where do we accounted this area variation? Area variation is, so what are the area variation that is happened? So that is the area into the height change is exactly equivalent to the small area, that is a larger reservoir area into the delta H, that is a change in the area is equal to the smaller tube area into the height. So that is actually the variation is happening in this particular tube. So our delta H can be calculated like this. So the delta H is smaller area tube to the larger area, that is reservoir area into the H2. So we can obtain easily delta H. If the area of the tube, if the area is very large and if the limb area is very small, if the limb area is very small, and if the capital, if the small a is, if the capital A is very large and small a is very small, if the small a is, if the small a is very small and capital A is very large, that means large reservoir are considered it. In that case, our delta H will become negligible. Our delta H will become negligible. In that case, A by A will become very small, and we can directly neglect the term in the delta H. And if you neglect that equation, what do we have? We have a simple, again, the simple mathematical equation of YouTube, or the single column manometer, the same expression has been obtained. If you compare the previous one to this one, so that we have obtained the symbol and the same solution we have. So now the question comes, when do I use this type of reservoirs and all that? When your variation in the manometers is very minute, when the variations in the manometers is very minute, and you are interested even in the small variations of this, even when you are interested even in the small variations of this particular flows, then we can introduce this type of reservoirs. So let us see the next type of manometer, that is the third one we have discussed about, that is an inclined manometer with a single leg inclined manometer. So as you can see on screen, the construction of a inclined manometer, that is these are all single column and single column vertical. So if you are seeing previous one, it is single column with a reservoir, and this is the case with the single column and inclined manometer. So nothing difference in this one. So the reservoir is also available, but the limb is inclined here in this one. But the limb is inclined in this. So only the limb inclination length is being added to this one. Only the inclination length is being added to this one. So when we are applying the equilibrium conditions, when you are applying the equilibrium condition at the x-axis, so the previous equation only I have brought it here in this one. Just see, but here my actually H2 is not equal to the H2. Here in this question, my H2 is not equal to the H2. Here my H2 has been changed. Here my H2 has been changed. So here my H2 is not the vertical component of the, here my H2 is not the vertical component. So here my H2 has become as L. So now I have to write the equivalent one. Now I have to write the equivalent one for my H2. So what is the equivalent height in the inclined limb to this one? So that is the component of the sine theta. So then it will become L sine theta. That will become L sine theta, which is being represented. L is equal to this, here H2 is equal to L sine theta. L sine theta, that is being presented here in this one. So that is L sine theta into rho to G. So H is equal to L sine theta actually because of this inclination which is made. So that theta has been accounted in this flow. So it has become PA is equal to L sine theta into rho into G. Now you may question, sir, what about this? What about on the other side? What is whether delta H we are going to discuss or not? So if your delta H is neglected, in that case, this is what the equation we are going to obtain. In that case, this is what the equation we are going to obtain here. Right, I am just equated to that one. So let us apply some numericals to this one. So to understand better about what exactly it is about, how do we deal about the manometers and how do we obtain the pressures in that one. So let me give you some simple examples for this one to find out the pressure inside the manometer. So here which type of manometer it is? It's actually the manometer with a reservoir. It's a manometer with a reservoir. You can see on the right limb and on the left side we have the pressure and again a reservoir, but the equilibrium level to that point A height, it has been given as 20 centimeter. And on the other side, the limb is open to the atmosphere and from the reference level. So that means here you just see the reference level or level of equilibrium, we have to decide it here. So this would be our equilibrium level. At the equilibrium level, above which we have 40 units above this one, and remaining it is open to the atmosphere. Right. So let us take this area of the right limb as small a. Small a, let us represent it as small a, and capital A is the left hand side. Let us represent it as small a, capital A. That is reservoir area and the limb area. And let us represent this right hand side, that is a limb, right hand limb, that vertical column with reservoir. Let us take this vertical column as H1, and on the left hand side let us take it as H2. That is the height available over there. Right. And now let us make the notations for this PA. The PA is the pressure available at point A. Okay. So then now what exactly the A by A is equal to? A by A here in the question he has given it as, here in the question it is given that single column manometer is connected to a pipe containing of liquid of specific gravity 0.9 and center of the pipe is 20 centimeter from the surface of the mercury in the reservoir, which has 100 times more area than that of the tubes. Yes, 100 times more than that area of the tube. Yes, it is being even represented in the figure. Yes, the mercury on the right limb is 40 centimeter above the level of the mercury in the reservoir. Now find out the pressure in the pipe is. Find out the pressure inside the pipe is. So already he has given that the area ratio. So what he has given is, so that is, he has mentioned which has 100 times more area than that of the tube. So that means reservoir area is greater than, so that is 100 by 1 actually. That is actually 100 by 1 which is being given. So that where capital A represents the reservoir area and small a represents the tube area. So where from that one, now what exactly we have to do? So let us find out the pressure on the right hand side and the pressure on the left hand side in order to apply the equilibrium conditions. In order to apply the equilibrium condition, let us take one equilibrium point. So where this 20 centimeter and 40 centimeter is being balanced here in this one. So first point, we have selected the fluids, and second point we have to apply the equilibrium point in this one. So that equilibrium point, that equilibrium level I am applying it on this one. So this, let us take this as our equilibrium level. So at the equilibrium level, so that is PA is equal to, that is actually delta H. So delta H means A by A into delta H2. So that is A by A into H2 is equal to rho to G. So how did we obtain this equation? So don't get confused here in this one. So the equations which you have obtained is by using the hydrostatic formula, simple hydrostatic formula, that is rho G H. That's actually rho G H. But here it is actually rho G delta H. So here we have said on the left hand side, it has a rho G, rho 2, G2, rho 2, G, H2. That is H2 is a delta H2. So directly I can't find the delta H2. So what I have done is delta H is equal to A by A into H2, that I have equated it here in this equation. Then coming to the other one, so that is rho 2. This is actually the formula which is involved or taken from the previous example or previous derivation. And next, the pressure available above this level, so that is rho H2, rho 2 into G minus the pressure at the point A. So it has already obtained the equilibrium position, that is H2 rho 2 into G minus rho 1 H1 rho 1 rho GH, rho 1 G H1, right? That's where the pressure is available on the, what we get the pressure on this one. Okay, so pressure on this particular one. So let us apply, this is what the formula we have framed for this one. So applying that numerical on this one, so we get the answer for the pressure available at the point A is equal to 5.21 Newton per centimeter square. Okay, now still if you are not clear about what exactly we are understood or what exactly the, let us spotlight on this one. See, so what is the pressure available on this one is PA, and A by A is actually delta H here in this one. A by A is actually delta H here in this one, right? So it is actually delta H, but delta H is equal to delta H by H2 is equal to A by A. So from that formula, we have obtained this one. So or else let us go back to this one and let us see there. So here from this previous one, this is what the problem related. So delta H is equal to small a by capital A into H2. Delta H is equal to small a by capital A into H2. This formula is being applied here in this problem or the numerical. So that is what I have applied with A by A into H2, that is delta H, into rho 2 G. Rho 2 G means density of this particular fluid into the G into delta H, minus, there is again one more variation because of the reservoir, very slight variation we get. We don't get a large variation. That delta H variation within the minute variation which is happening in this one, and the other one is directly due to the pressure available on this particular fluid, that is due to the 20 centimeters. Due to the 20 centimeter directly, what is the pressure available on this one? So that is rho GH, rho 2 GH2. So then minus H1. So this is the equilibrium, at the equilibrium level, as it is open to the atmosphere, we are interested only to find out the gauge pressures here in this one. So directly applying the formula, so that is actually equal to, so but we have brought it on this side, so it has become a minus H1 rho 1 G, H1 rho 1 G. and applying those and substituting the numericals which is given here in this one. So the specific gravity of the liquid is being given as a 0.9, converting those one, and the area is available, that is 1 by 100, and H2 is 0.4 as it is given in the units of centimeters. So we need to convert it into meters. We need to convert it into the meters. And directly the rho 2 is not given here in this question. The rho 2 is not given directly into the question. So but the rho 2 is considered as a manometric fluid. So in that manometric fluid, so that is manometric fluid, that is a water which is 13.6 times of the water. So that from that one I have brought the density of this water. So that is 13.6 into the 1000 into G is 9.81, and minus the rho 1 G. So the rho 1 for the rho 1 liquid, they have mentioned that it is 0.9 times of the specific gravity, 0.9 times of the water. So from that one we are getting it as 900 into 9.8. So that is actually 0.9 times of the water. So that is 900 into 9.81 plus what is the H2? They have given it as 20 centimeters. H2 they have given it as a 20 centimeters, that is 0.2 meters again. 0.2 meters into the rho 2. Rho 2 is actually given as, now rho 2 is given as a, what are the fluid which is available on this side, right? So that is 0.4 into the rho 2 of this particular fluid into the G, right? Minus H1. So the H2 is 20 and H1 is, so here we have made, so H2 is 20 and H1 is 40. So we have to substitute in this equation and finally we'll get the resultant equation for this particular fluid flows. That is what the solution we get it is PA is equal to 5.2 Newton per centimeter square. PA is equal to 5.2 Newton per centimeter square. So now let us look clearly, let us understand better about this differential manometers. Let us go for the next topic, that is about the differential manometers. So differential manometers are resultant. The differential manometer resultant will give you only the difference of the pressure, but they will not allow you to find out the pressure at any points. They will not allow us to find out the pressure. And what are the types of differential manometers? So that is on the second part of this particular manometers. We have come to one side branch we have completed, and the second branch we have started with here in this. And on the second branch side, we have this differential manometer, and the differential manometer types are two piezometers, inverted U-tube manometer, and U-tube differential manometers, and micromanometers. These are all the different types of differential type of manometers. So remember my point, these are the different types of differential manometers. So when it is a two piezometers are, as you can see on the screen, so just two tubes are connected at point A and point B. So when they are connected and when they are resulting pressure varying at the point A to the point B, so what that would be the difference in the pressure which is noted by arranging the tubes in this way is called as a differential, or the two piezometers, that is called as a piezometer. So how do we get the pressure in this one is rho G HA. So rho G HA minus rho G HB. So that is what the difference in the pressure in between the point A and point B. We can obtain that solution. So let us talk about the inverted U-tube manometers. Let us discuss even about the inverted U-tube manometers. So as far as the inverted U-tube manometers are concerned, here we can see, so this is what the construction involved. So till now we have seen the regular manometers. Now let us see about the inverted U-tube manometers, how the construction of the inverted manometers is. So the construction would be similar to the previous one, but they are completely inversed. Completely they are inversed in the direction, right? So let us take the U-tube manometer, and here the brown color indicates the manometric fluid, and PA and PB are the 2 points of where we are interested to measure the pressure. Now rho 1 is the density of the fluid on the left hand side, and rho 2 is the density of the fluid on the right hand side. And now what is the say? First immediate point we have identified the fluid, and second immediate point I told you that we need to go for the equilibrium position. So where do I spot this equilibrium? So where the manometric fluid is balanced with this fluid on the other side, that I have to present with an equilibrium position. So let us represent this as an XX. So where I need to consider this manometric fluid equilibrium, where the equilibrium position is being considered. So now referring to this particular point of the equilibrium, that is XX point. So let us equate the fluid. So that is, let us bring the fluid into the equilibrium on both the sides, that is PA is equal to PB. So now obtaining that equation, so we have on this side, that is, so that is the pressure available on the side left hand side, that is PA, and when And what is the height available in this one? So what is the height available on this side? Let us represent with the y1, and height available on the right hand side. Let us represent it as y2. Now it is actually, so now PA minus y minus has come means from the equilibrium position we are moving downwards now. From the equilibrium position we are moving downwards. When you are coming downwards it is being negative. When you are moving upwards it is being treated as positive in our notations, which is following from the earlier of this particular sessions. Okay, so from that one when we see, so according to the hydrostatic law, again we can write it P is equal to rho GH. P is equal to rho GH. On that formula we have written that, so that it is equal to rho GH. So where rho is rho 1 and G is capital G, and H1 is actually equal to here Y1. Then next, what about the manometric fluid? So at the manometric fluid is positive at the equilibrium position. So here there is only 2 points. So one, it is because of this fluid available, and second one is due to the pressure available. So moving on to the other side of this particular equation, so there from the manometric fluid there is some height variation again. So there is some height variation on the manometric fluid. So let us represent that height also. So let us represent that height as an x. Let us represent that height as an x. So then again the fluid level above this one we will be calling it as rho G H. Again applying the same formula here, but as a manometric fluid above this particular, so that is being considered as positive. So one side when it is being considered, on the other side it is also positive on the other side, it is also negative on the other side, but we have brought it on to the left hand side of the equation, so it has become positive. It has become positive. So that is PA minus y1 rho 1 plus x into rho m. So that is rho GH actually. The formula we are following initially, that is rho GH. So sorry, P is equal to rho GH. So here the G is missing in this term, so G is taken out common here and all. Right. And another one, so from the equilibrium level we have another height, but the liquid or the fluid is different from this. So that has become y2 rho 2G. Y2 rho 2G. So on equating this at the equilibrium level, we get the difference in the pressures in between. So that is PA minus PB is equal to rho 1 y1 minus rho mx minus rho 2 y2 into G. This is what the equation is resulting, which is measuring the difference in the pressure by using the inverted U-tube manometer. So what is the difference in between the regular manometers to the inverted U-tube manometers? Is we have to notice one point here in this one is, here when the points are inversed from the equilibrium position, when we are moving downwards, it has to be taken as a negative. Only that notations, if you are following it, then U-tube manometers are also similar to the application of the equation is similar to the previous one. Okay, so then let us discuss about even the differential U-tube manometer. So as you can see on the screen, both look similar, but these are called as a differential U-tube manometers. How they are differential? So, but as far as the word of the definition is concerned of the differential U-tube manometer, they are used to measure only the differential pressures. They are used to measure only the differential pressure. Now, these are the inverted or the straight manometers. Yes, they are straight manometers and U-tube type. And here, X is the level of the equilibrium. So by this time, you might be easily noticing where the equilibrium need to be applied. So, at the manometric fluid, where it is balanced with the fluid, or where the interference is available, at that point, we will be drawing the equilibrium position. So now how they are differential and different U-tube manometers. So here we have two categories in this one. So one, it is having a two pipes at a different levels. Another one, we are having a two pipes at the same level. One is having a two pipes at a different level, and another one we have a two pipes at the same level. So when you have at the different levels, so above this manometer you can see the point A and point B are different. Point A and point B are at the different positions. And whereas in the second case, point A and point B are at the same points, but the liquid field inside is different. Two manometers are at the same point it is measuring, but PA side and PB side the liquid is going to be different, right? So that is what exactly it is, the difference in between. So let us obtain the solutions for this. So first, what we have identified the liquids. Here there are three liquids in this. So the previous examples we have went within two liquids, and in this current example within a differential U-tube manometers, we are going within three liquids or three types of fluids, or three types of liquids. That is rho A density fluid, rho manometric fluid, and rho B type of fluid. Similarly, on the other side, rho A type of fluid, rho B type of fluid, and rho M type of fluid. So there are three fluids in this. So let us see on these two pipes at the different levels. So applying our equilibrium position at this XX. Applying equilibrium position at the x-axis, what we get is, so that is applying equilibrium position at this x-axis. So directly we have the pressure at point A, that is PA, the pressure available at the point A, that is PA, and here if you notice, this completely, this is at the height above this one, and if you see, so that h height plus x, so it is not the h plus y, because we are talking about this left side limb, we are talking about this left side limb, so it is the total height of x plus h, but the liquid is same, the liquid density is same, so that is represented with the rho 1 g into h plus x, rho 1 g into h plus x. Now coming on to the right hand side of the equation, where it is directly PB, where it is directly PB, and now, so where it is directly PB, and because of this manometric fluid is only up to this point, because the manometric fluid is only up to the height of h, it has separated from that, that is rho m gh, that has become rho m gh. And now above this one, there is again other density fluid, that is the third type of density fluid, which is given rho 2 g into y, rho 2 g into y. So on obtaining this one, we will get the equilibrium equation for this particular fluid flow, for this type of fluid flow up to this height of B we are accounted in this. Okay, so from that one, taking out the PA minus PB, so that is the differential pressure by using the U-tube manometer, two pipes at the different levels, we can obtain the solution for the what are the pressure acting in this one, what are the pressure acting. So only logic is involved in this. So how do we balance at the equilibrium position and whether we are accounting correctly or not, that we have to take care. Now let us see on the other side of it, two pipes are at the same level, two pipes are at the same level. So when the two pipes are at the same level, so here again similar to that one, balancing on the two sides of the equation, that is PA, pressure available on this side PA, plus if you see on the PA side, it's a total height to the point A is same fluid or the same liquid is available, where the height is h plus x, where the height is h plus x. So we should not forget this, here it is same liquid. So that is the reason it is rho 1 g. So A side we are representing with the rho A g. H plus x is the fluid, that is hydrostatic law we have applied, and we have obtained the pressure on this side. Now moving on to this other side of this one, so that is moving on to the B side of the fluid. So here we have directly the pressure available at this point B is PB, plus if you notice it here, so we have two types of fluids above this equilibrium level. So one, it is up to the height h, so for that reason it is rho manometric fluid density into the gravity into the h, that is h is up to this height only, up to this height only it is h. But if you forget this one, then we are not able to get the balance equilibrium. So what is the above height h? So above height h is, it is having a different fluid, so that density is rho 1 g x. So this, by this way we can get the equilibrium equations, and people will be calling even it as a differential U-tube manometer derivations also. So the derivations are very simple. So this is what the approach when you go for the problem within a differential and the U-tube manometer, this we are going to get within a final resultant of the equations for the single column manometer, differential manometers, U-tube manometers with the differential U-tubes at the same level and at the different levels. Okay, so I guess you can approach to the numericals even. So we